I guess that's the comfortable way. I try to fix this by telling it that it should not use low data mode. Let's see. Well, okay. I guess we cook with what we have. All right, so today was supposed to be this awesome class about starting to talk about online. Learning. Online RL. Still going to be awesome, but we lost a bit of time. And is online RL. So at the beginning I said that, okay, we're gonna have 3 topics: planning and batch learning and online learning. Why are these children of planning? Well, maybe because they're a little bit harder than planning. And of course, we are recycling algorithms between these settings. The major difference between these settings, just to remind ourselves, is that here we care about compute. And we mostly interact with a simulator. In the batch setting, we care about sample efficiency. And that's because we are not interacting with the word, but learning from a batch of data. And finally, in the online setting, in a way, we care about sample efficiency. So I put that into quotation marks, because we are going to define sample efficiency in some way. Wow, such a big lag. This is gonna be funny. Wow, okay. This is really a huge lag. Anyways, sample efficiency. And this is interactive learning or live. So in this setting, you have a learning algorithm, the learner. Some people like to call that the agent. I don't know. What's an agent? And it's interconnected with this environment, which we're going to model as an MDP. Just stay in the realm of MDPs. It's gonna be fun enough to consider this setting. And we just want to understand how good a learner can be in this interconnected setting, but the learner is receiving these observations about states and rewards, and it's sending actions to the environment. Oh, the lag is much better. So when posing a problem, we should first agree on what is a good metric to use to evaluate and compare different algorithms. So these are the algorithms that we want to design. We want to compare them across different environments. There are different notions that people use for this purpose. And today I'm going to talk about that, and in the rest of the lectures as well. So how good is a learner? We're going to evaluate learners based on their regret. In a nutshell, we want to say that the learner is better if it collects more rewards. Is intuitive, right? So that's the goal of acting in the environment, to collect reward. The more the reward is, the better it is. There's a basic assumption about this model. But to be able to compare algorithms across different environments, we don't want the comparison to be spoiled by shifting the rewards by some constants. So if I add, 2 to every reward in some environment, then suddenly every algorithm in that environment seems to be doing better. But that's sort of not real. It's not a real advantage for the algorithms, because all of them are doing equally well. So to facilitate comparing algorithms across different environments, we want to somehow cancel out these constant shifts. But what is the right constant to use? Here the proposal is to use as a constant that is specific to an environment that, shifts the performance metric, the value of the optimal policy, like how much the optimal policy would be making. Actually, we are already pretty familiar with this, because in the context of planning, when at the end of the day our algorithms came up with the policy phi hat, then what we were doing is that we compare this to the star. We compare the value function of pi hat with the optimal values. And we wanted this to be small. So compared to being, what are we doing? And so that's the notion of regret. And so in planning, we have already been doing this. And this notion in the context of planning, this is sometimes called simple regret. I'm not sure whether this is a very good name for it, but it kind of stuck. This wants to make a distinction between that in the online scenario, the learner is constantly collecting reward. And so in this case, there is no final policy that the learner would output, but we should directly compare the reward that the learner is collected with, ideally how much reward you could have collected. And so that's the notion of sometimes also called cumulative regret. To contrast it to the simple regret, which is kind of not cumulative. So cumulative just means that you're accumulating over time reward, and as a result, if you're not doing a good job, then you close. No? Oh, yeah. So I guess all of these apps randomly decide that it's okay to send me notifications, even though I never consented. Anyways, so over time, when we're talking about regret and online learning, usually we don't think about the discounted setting. You can define some notion of regret in the discounted setting as well. But usually we just like forget about discounting. So we study the undiscounted setting. And if you study the undiscounted setting, you can do that in many like subsettings. So one of the subsetting is the case when learning is ongoing, it never stops. There are no episodes. So that's the infinite horizon setting. And in this infinite horizon setting, what is an optimal policy? How do we define an optimal policy? We never talked about this before. But what makes sense is that maybe as a first order approximation, it makes sense to think about the average reward collected per timestamp. And so you want a policy which maximizes the average reward per timestamp. And you want to compare to the performance of that. But you can also set it up in such a way that like you have this rolling horizon for every horizon n, that is the optimal policy, and this is how much reward it would have collected for that horizon. And my learner is collected this different amount, and the gap between the two is going to be my regret. So in this case, so you could do that. So you could have something like that the regret is like n-step optimal from the start state versus how much reward I collected in n time steps. And then maybe take expected values because these are random quantities. Or it could be another alternative is to use this optimal average reward. So this is optimal average reward. And then just say that like, okay, like supposedly this optimal, an optimal policy which delivers this much optimal average reward in n time steps should collect reward close to n times the average optimal reward. So there is a law of large numbers there in the background. Indeed, an optimal policy for this setting would collect reward, which is pretty close to that. As the horizon grows, the n-step optimal policies are kind of like not doing much better than the infinite horizon average case optimal policy is doing in terms of the rewards. This is for the setting where all these concepts are well defined. Anyways, the comparison is still with respect to the reward that was collected to the learner, collected by the learner. So this is another alternative, and mostly people just use this. So that's for the infinite horizon setting, and the caveat here is that row star may not even be defined. So in order for row star to be well defined, you have to have some restrictions on the MDP, because maybe from the initial state, you go right, you get to some part of the MDP, from which you cannot escape anymore. There you can get some average reward, optimal average reward. Or you go left, you get some other part of the MDP. You cannot escape from there. You cannot go to the other part. And the average optimal reward in that part could be different. So in the multi-chain setting, you have to be a little bit more sophisticated with your definition of regret. So that's the undiscounted setting. No, sorry, that's the infinite horizon undiscounted setting. And then there is the finite horizon or fixed horizon. Setting, which we have seen before. So in the fixed horizon setting, you have episodes of a fixed length. Let's call it capital H. And within an episode, there are these stages that the learner goes through from indexed from 0 to H-1. Next page, please. It's coming. Just takes a bit of time for it to set up all the data, I think. Maybe if I stop writing, then it will catch up. I created a new page, that's why it's, oh, it's way behind. Okay, it's coming. There you go. Anyway, so you have these episodes, and you have a number of these episodes. So the episodes could be, you know, indexed from, I don't know. Okay, so this is dangerous. I usually use n for the number of episodes as well, but the literature likes to use k, so let's try to switch to k, and let's try to see whether I'm going to remember that I switch to k. Please remind me if I write n somewhere, it should be capital K. So this is the number of episodes. And what happens is that at the beginning of an episode, I don't know, little k, from some initial distribution, the initial state is sampled, and then the learner generates some actions. First generates an action for this state based on its past experience that leads to a next state. Then the learner generates a new action. And it goes on until the episode is finished. And maybe for the sake of creating a more uniform situation, let's also assume that after making the final transition, after choosing the eighth action, although the next state's value is not going to matter, the next state is also given to the learner so that we can create a more uniform situation. So here, the state at stage H+1 follows the distribution from this underlying MDP, where the state is the previous state and the action is the previous action. So you're in this MDP that has the states, the actions, transitions, and rewards. And I didn't add the rewards because, well, you could add random rewards, but for simplicity, And just for the sake of simplicity, so let's assume that given the states and actions, we can calculate the rewards. Like, yeah, the agent has an internal mechanism to get the rewards from the observations. So R is known. So then this is the experience of the learner in the case episode, and the regret after K of these episodes is going to be defined as the regret for each of the episodes, which is defined as for each of the episodes, that is the optimal value function for the 8-step setting. And there are 8 steps to go. And we take the optimal value for the initial state. This is the maximum value that the learner could have gotten if they followed an optimal policy, but maybe they didn't. And so they got some rewards. And this is how much reward they got. Okay. So this is the regret. And this is what the learner needs to control. All right, does this make sense? So we're going to mostly focus on this notion of regret and this setting. There are other ways of evaluating learners. So the sample complexity would look at basically something like this. So going back to the planning, so you can think about that the online interaction is also like a planning problem, because maybe at the end of the interaction, you need to output a policy and then learning stops and then there is no further learning. If that is the setting, then it makes more sense to measure performance with respect to the simple regret. And then the results are going to be expressed in terms of like how small you can make the simple regret with so many samples, or inversely, you can ask how many samples do I need to guarantee that the simple regret is going to stay below a certain threshold. So these are the sample complexity or PAC results. The PAC comes from probably approximately correct, because we can think about the policy that is being outputted as approximately correct up to, let's say, an epsilon accuracy. And the guarantees come in the form of high probability bounds that say that with high probability, we can guarantee that the algorithm outputs a policy which is approximately correct. So that's the PAC setting. You can convert between regret and PAC, back and forth. And the conversion loses optimality, I think probably both directions. I'm pretty sure about the PAC to regret conversion definitely does lose optimality in terms of dependence on time or number of episodes, but it's still a conversion. It's like, there is a nice paper by Christopher Dunn, Torla Timur, and Emma Brunskill, which talks about this conversion of different notions of regret. There's some regrets, like there are some different notions of like how well you're doing in MVP in an online setting. Some notions can be converted, others cannot be converted, but if you're setting up things carefully enough, then you can convert. I kind of like regret because it's like a very natural notion. Just you care about how much reward you collect. But if someone, like, it's a slightly different problem to optimize the simple regret than to optimize regret. So there can be differences in terms of how you design algorithms for them. In the simple regret case, you don't care about how much reward you're losing. You care about the information that you collect about how to act in the future. Whereas in the case of regret, you really do care about how much reward you collect as you go. So you constantly need to balance information needs and reward needs. And I'm pretty sure that everyone heard about this explore-exploit trade-off, which just says that learners which are too greedy either way are not necessarily good. So learners that take for granted whatever information they collected and just like act optimally with respect to anomaly estimated MDP, for example, these are called the greedy learners. They're not necessarily good. The simplest setting where this is easy to demonstrate is the MDP, where the episode length is just 1. So this is also called Contextual Bandits. So bandits are those MVPs where you don't plan for multiple steps. You don't care. As a result, you only care about the reward. You don't care about the dynamics. You already started always. And so, right, in the contextual MDP or contextual bandit case, if you have a single state, that's the simplest case. So that's like classic finite term bandits. So if you add to this that there is only one state, then you get finite term bandits, which only makes sense. By the way, all of this only makes sense if the reward is unknown. Otherwise, there would be nothing to learn about. But in the MDP setting, it's like the most of the complications coming from learning about the dynamics. So that's why I said that I'm going to assume that the rewards are known. Pretty much everything that we say can be extended to the case when the reward is unknown. So when the reward is unknown and you are in this bandit situation, then you have these actions that you can try. You see the reward of the actions in noise, the mean reward. And you can't be greedy because if you just think about the Bernoulli case, you may start unluckily with the optimal arm having a Bernoulli reward, but you only see zeros because you were unlucky. And then you will never ever try it again. Like, let's say after one pool. So that definitely doesn't work. You have to explore, and then people usually bring up a simple way of adding some randomization, like uniformly throwing in one action and whatnot. There could be a propensity of how frequently you're throwing in this uniform random action. So that leads to these epsilon greedy policies, and then there is a lot of pondering about like how good epsilon greedy is. Well, if you take bandits, then epsilon greedy in a worst case can only get you n to the 2/3 regret, or k to the 2/3 and n to the 2/3 regret. So epsilon greedy with not a So if you get very sophisticated with epsilon greedy, you can like simulate any other algorithm almost. But with no sophisticated tuning, like a priori choose an epsilon, then the best that you can get is n to the 2/3 regret, whereas better algorithms exist, the ones that we're going to talk about, that can guarantee a square root n regret. So you can see that the regret here is growing, but it's because it's cumulated, right? So the average regret, that would be like you have the cumulative regret over k rounds of interaction. The average regret would be rk divided by k, the average per episode regret. So if you have something like square root k, then regret, cumulative regret, that means that the average regret per episode is 1 over root k, it goes to 0. So that means you are learning. So that's good. Like in the limit, when k goes to infinity, then you're as good as the optimal policy. So we're very happy with any growth of the regret, which is below the linear growth, because then after that, if we divide by the number of rounds of interaction, then we get something that converges to 0. So sublinear regret is the goal, and the slowest the growth is the better. And so here, epsilon greedy kind of fails. So you want robust algorithms, right? So a robust algorithm would mean that, like in the worst case, it still works well. And epsilon greedy fails that test. There is no way of making that nicer. Yet people like epsilon greedy because it's simple, and we have to give like epsilon greedy that credit. It's super simple. It's already not that bad compared to that. How simple is that? And complexity does matter. And then sometimes when you get into a much more complicated scenario, you have functional approximation and whatnot. And we should keep in mind that there could be some real trade-off between computational cost and regret. And maybe epsilon greedy will have a comeback then, right? Maybe in some scenarios, it could be the optimal algorithm. Who knows? So we can't just discard it altogether and forever just because in some simple environment, it achieves something a little bit worse or much worse than some other algorithms. But it's still interesting to look at the other designs. Like what is the algorithm? Like you have to be curious about like what is the algorithm that achieves this square root, and maybe in the more complex scenarios that algorithm still going to cut it. So these algorithms, there are many of them, but a lot of them are based on the principle of optimism in the face of uncertainty. And this is a general principle that applies beyond bandits, beyond MDPs, to other scenarios as well. For optimism in the face of uncertainty to work, the necessary condition is that if optimism tells you to try something, then you should be able to learn about what you tried. So you should be able to get information about what you tried. So trying something gives info about how good this something is. So this something could be just an action, could be a policy, depends on the situation. this is a necessary condition and often sufficient as well, although optimism may not be a very good choice in scenarios that you get more information than just the value of the thing that you tried. So for sufficiency for optimism to be optimal, this is not a theorem. This is more like an observation, because it's too vague to be a theorem. But it seems to be true. Is that whenever you try something, trying X, if it doesn't give information about, or much information, some other option that you could have tried, then optimism is likely to be a good choice in terms of like no other algorithm may do better. But if this is not the case, and this is important to remember, then there could be algorithms which will outperform optimistic algorithms. Probably outperform. Anyways, so that's the honest evaluation of how good is optimism. Well, one thing we like about this optimism in the face of uncertainty principle, before we know what it is that it still applies quite generally. So it leads to pretty good baselines for a lot of different diverse settings. And people were successful in demonstrating this. So what is this optimism in the face of uncertainty? Think about it in the context of that you have a probabilistic model of how the world works, like an MVP. That's a probabilistic model of how the world works. If you have that, then you can list all your models, collect them in a set. So all the possible worlds. And optimism in the face of uncertainty works by saying that, well, given some data that you collected, you can rule out certain words as implausible, not too likely. It is literally, usually this ruling out is based on the log likelihood of the data. So if you observe that the data, like under some word, some setting, some model, the data that you observe have a low log likelihood, then you would say, not good, this is not plausible. So then you have the plausible words. And once you have the plausible words, the way to figure out how to act works by choosing the word in which acting gives you the best value amongst all possible words. So for every word, let's say you have this initial state fixed, let's say you're in an MVP. Then you would say that, okay, like from this initial state, if my transition probabilities were such and such, what would be the value for this initial, like the highest value that I could get for this initial state? It depends on the transition probabilities, and you can evaluate all the models. So that creates kind of like a pressure that's like, like maybe the values are growing, and this is the value that you're trying to keep high. So that's kind of like the return, the total reward within an episode or on the average. So that creates this pressure, and then you choose the word in which you get the best value. So it's going to be this word. And then you choose the behavior that generates this best possible value, so the underlying policy. And you would just follow this policy. So this is what works in bandits, this is what works in MDPs, and this is what works in like more complicated scenarios as well. This works for when you have structured models, when you have less structured, like today, time permitting, we're going to talk about just a tabular case. Your model is just like this big transition probability tables. It's the instantiation of the same thinking. All right? So once you have this, then you follow the policy. That gives best value in the best word. So it's going to be an optimal policy in the best word. So it's a max-max problem. Max over plausible for the words, and max with respect to all the policies. This could be one of the challenges that, so sometimes it's called optimistic planning, that this is just maybe computationally intractable. In some cases it is. Some other cases it's not. But yeah, you have to keep asking the question, is this tractable? And then if it's not tractable, maybe you can come up with tractable approximations that don't lose too much compared to the best possible solution. So this is more like a heuristics of like how to design algorithms, and then people deviate from this pattern to make their strategies tractable. The other choice that you have is like how you define the plausible set of models. And there's where tractability is going to come up, like depending on how you do that, you may end up with a tractable algorithm or an intractable one. And if you make these set of models, the plausible set of models smaller, then you tend to get better algorithms. So a large portion of the literature deals with how to improve in terms of what we, how we define this set of plausible words. And yeah, like there's a lot of activity on that. All right, so this principle probably was discovered by a couple of folks. Lloyd and Robbins definitely had a paper that was, I think, in '85, where this principle appears very clearly. There is a follow-up paper by Karehakis and Robbins where it's even more clear. And they call it the principle of optimism in the face of uncertainty in that paper first. And then there's been a lot of work. In the control literature, I think it was independently discovered by Kumar in '83. And then there were follow-up works to that line of thinking as well in the control literature. So it's everything that is a versy idea. It's being discovered all the time. So it's good. All right. So let's do some concrete, specific math to fill this with contents. Because so far it's a lot of words, like lots of philosophy about like how does this work? And in the remaining time, I probably don't, I don't want to keep you guys for too long. So in the remaining time, I will only probably have time to introduce the algorithm and maybe discuss some questions around the algorithm. So we'll do this in the fixed horizon episodic setting that was outlined above. And why I wait for, okay, I don't have to wait anymore. But I wanted to ask, like, do you guys have any general questions for what I presented so far?
So maybe I'm not too familiar with this, but why do we maybe care more about regret optimality than like pack optimality? You said that there's not a one-to-one between the two settings.
Maybe it's historical reasons. I don't know. I find regret more interesting, personally, but that's like, who cares about that? I don't know. I think that people are intrigued by this notion that you pay as you go, and you're continuously optimizing, and you have to resolve this trade-off between the need for information and the need for the reward in a smooth fashion, rather than go in and just collect information and then stop. For practical applications, I don't know. Yeah, so Connor says that pack introduces more parameters, more complex state. Yeah, somewhat. Well, we're going to have a data. So we have n and data, and they have epsilon and data, and then n and. But yeah. It's for practical applications. Yeah, I don't know. So first of all this is about online learning, and I wish there were more applications, but anyone who ever saw these algorithms doing their things must be questioning whether it's a good idea to apply them in an online fashion. So you can only apply them if, you know, safety standards are met and whatnot, right? And online learning has the advantage that you're interacting with the real thing. So if you are trying to train a robot to accomplish some task, you can try to build a simulator, or you can try to collect data. But we have seen that collecting data is not too promising. If you stop doing that, like if you can't go back and then collect multiple rounds of data, then that's not necessarily the best thing, right? It could lead to like some pretty big headaches if the data was not, you're not lucky with how you're connected the data. If you didn't know where to look for the solution, then likely the data is not going to contain enough information for you to discover very good solutions. So that's for the best setting. And for the planning setting, your simulator may be off, and so maybe you need an extra loop that kind of tunes the simulator and whatnot. But then you're again back to the online setting. So at the end of the day, you really need to, if you want to apply these algorithms, then you probably at one point or another, you should consider the online setting, even though it looks extremely dangerous to, you know, let loose a learning algorithm in an environment. But you can create some boxes for these algorithms, and then that's what I would do, like by default, that, you know, the robot's torque should be limited so that it doesn't break out of its box, and like be sane when you're designing things. Right, so the pack setting, I guess it's just like people got attracted to the cumulative regret setting. I'm more attracted to it for whatever reason. But also because the designs can be converted from one to the other, it doesn't matter that much. So the automatic conversion loses, but oftentimes the same algorithm with a slightly different tuning is a good algorithm for the other setting. So it's like, I think that people develop the notion that like, yeah, it's enough to look at one of the settings because we can figure out the other setting as we go. Yeah. And there is also this notion of like, oh, you want to build an AI that constantly learns in the environment. So that's better supported by the notion of cumulative regret. Right. Other questions? Oh, funny. What's the context of? You guys have a discussion here. Packages. Okay. Go ahead.
The whole world is just sometimes optimism is all about how much reward we can get. But for all those words, for all those MDPs count, they also be different in transitions.
Right. They are. Actually, the case I'm going to look at is going to be when the rewards are shared and they are the same and they are known to the learner, and the only difference comes from the transitions.
Well, thanks.
It's true. It's true. Okay. Great. So we have this MDP with its states and actions, and I'm going to put a star next to the transition probabilities if I'm talking about the MDP, because I need some way of denoting this. And so how does the algorithm work? So we want to instantiate this this idea in the context of this fixed horizon setting. So we will have these episodes going from 1 to, I don't know, capital K. And at the beginning of an episode, the learner already collected some data. So you fix some K. Well, at the very, very beginning, maybe there is no data, but okay, if there is some data, then the learner doesn't know P star, but knows R. So that's a setting that I'm looking at. So the simplest idea then is to estimate P star just by taking empirical averages. So we could do the following. So we can just say that let's estimate P, and so for a given action and a given state in this episode K, our estimates are going to be, we're going to count how many times, okay, so for a concrete specific probability of transitioning given action A from state S to state S prime, we can count how many times up to now we have seen this transition from S using action A to S prime, and divide that by the number of times we have visited the state action pair. So just simple averages. So this notion of this V notion, that's my abbreviation for taking the max of two numbers. And so here I'm just trying to prevent dividing by 0 when you have not encountered yet the state action pair. then you don't want to divide by the number of times you have seen that state action pair, then it would be divided by 0. So you divide by 1. What are we dividing in this case? Well, we are dividing 0. So in this case, we get all zeros. So it's like, in that case, we don't get a proper transition probability. These probabilities don't sum to 1, and you're summing them over S prime, but it's not going to matter. Because we're not going to just go with these transition probabilities, but we're going to put confidence intervals around them. So here is what comes of computing what's plausible and what's not plausible, right? So what are the plausible models? So to instantiate this optimism in the face of uncertainty idea, we have to calculate what are the plausible models. So this is going to be all those P's. These P's are just these transitions, such that for every S and A, state action pairs, it holds that if I take, so as usual, if I don't write the S prime, that means the probability vector. So if I take the estimated transition probabilities, I'm going to allow all those transition probabilities which are not too far. How far? Well, this is going to depend on how many times I have seen this state action pair. There is going to be this beta function which takes natural numbers and returns non-negative numbers. Well, I guess numbers bigger than 1, but okay, whatever. It's positive numbers for sure. And we're going to choose this in such a way that we don't include unduly models that we don't want. So you want this this set. We want two things from this set. One, so our goal of choosing beta is twofold. One, we want P star, the optimal transition model, like the true one, to be in the confidence sets for every K, every episode, with, let's say, probability 1 minus data. So we're going to fix, like, the algorithm is going to have some parameter data. And we want to guarantee that with probability 1 minus data, this algorithm works well. Okay? And then we can talk about how this results in controlling the expected regret and whatnot. So just start with high probability guarantees. So this is the first property. And then the second one is that, well, CK is not too large. This is a little bit undefined at the moment, but we will see that the larger C is going to be a little larger beta. If you make beta larger, then the C becomes a thicker set. It's a bigger set. It's monotone increasing in beta. And the reason we want this is because the smaller you can make this set, we'll see the better the regret bound is going to be. Oh, you may ask, what is this norm? So this norm is going to be the 1 norm. Why then 1 norm? Well, it's a very good fit for the analysis. Generally, when you are comparing probability distributions, the 1 norm is a good choice. Because then the averages with respect to the probability distributions are going to be uniformly well controlled. So if you have an average with respect to some distribution and you have another distribution, 2 distributions are close in 1 norm, then that means that the 2 averages are also close. And we all that we care about are these averages, right? With respect to the transition probabilities like that comes from, like writing, like what's the notion of reward and like expected reward and return and all that. So on this, two things. And once we will choose this beta in some ways such that it's as tight as we can with simple tools, and we meet this high probability guarantee. And once this is done, then comes the optimistic planning part. So it's choosing the optimistic model and choosing as well the optimistic policy. So what does this correspond to? It corresponds to choosing the policy, a policy, and this is going to be the policy that we're going to follow in this round, which is going to be the age horizon optimum policy. For the initial state that we have. Well, it could be for any state for that matter, but it's for the MDP that is optimistically chosen. So for the MDP corresponding to the transition probabilities that are optimistically chosen. So what is this? Like P tilde K. So that's the argmax over all the transition structures in CK. And what are we maximizing? Well, as I mentioned before, we are maximizing the optimal value and the transition probability with respect to the initial state. Right? So at the beginning of the episode, you observe this initial state. So in principle, well, these are well defined, at least, as objects. And you might ask, and we should discuss whether this is this can be implemented in a computationally efficient way. Whether we can find this policy and these optimistic transitions. But so far, it should be clear that this is just implementing the principle, right? So we decided about what is the set of plausible words. This is the set C of K. And amongst those, we choose the best possible word, which maximizes the maximum value, while with respect to the initial state where we are starting from, so we care about that state. And then we just take the corresponding optimal policy. And to finish up the description of the algorithm, so then just follow pi of k. Well, I don't need to put this up there, like just lower index is fine. Up to the end of the episode. And I repeat. Okay, so one thing that is a little bit unfinished yet, well, many things are unfinished, but one little thing that we should at least take off of the list of unfinished things is that at the very beginning, when k equals 1, of course, all the counts are 0. So you have not seen any data yet. So this transition probabilities, the estimated transition probabilities are going to be 0. And what should be the beta? So what's beta of 0? So when nk is equal to 0, then that goes here and beta 0. what should be beta 0? Well, the answer to that is that hard. Beta 0 should be 1. Because then that's going to guarantee, we don't have any idea about what the word is, so we want to include all the transition probabilities at the beginning. Okay, so this way of writing things, by the way, is really should support the idea that these transition structures are state action based. So the state action pairs are the units, and you should be thinking about, okay, what for every state action pair, what is the next state distribution? And you're kind of independently reasoning about each of these, and that's how you compile a bigger model, right? So in a way, we have this product structure of these models that we can independently of each other reason about every state action pair. So for some state action pairs that you're visiting quite often, you will have a lot of information about them. For others, you don't have any information yet. And then there, the model is absolutely permissive. It's going to say that, well, all transition probabilities are gained. And so the beta 0 equals 1 allows in all the transition probabilities, because in this case, the estimated transition probabilities are the all 0 vector. And so here we are allowing all the transition probabilities, which are at distance of 1 from the all 0 vector. Well, and this is just the set of all transition probabilities. Okay. All right. So my time's up. I didn't get too far, but at least we covered the algorithm. So the next step is going to be maybe choose CFK, and then we're gonna see how big is the regret. We're gonna have some fun deriving a bound on the regret of this algorithm. Right, but I don't think that it's appropriate to go into these. Sorry for losing a lot of time at the beginning. It's a bit disappointing, but I don't want to hold anyone for much later. And both of these are going to require some time. It's not like that I can be done in 5 minutes. So, but we can have a discussion maybe if you want to hang out a little bit more. I'm happy to hang out and we can discuss things. Right.
I have a question about beta. So is it decreasing in n?
Yeah.
So when n equals 1, then p becomes a probability vector. So in that case, isn't it possible for it to be the L1 norm to be greater than 1? And you might still want to keep it around?
Well, yeah, okay. So I think that, okay, eventually, right. So it has like a numerator and denominator, numerator, denominator, and I think it's decreasing the way it's constructed, and it's gonna work out, but it's at the outset you wouldn't need to necessarily constrain it to be decreasing, but it happens to be decreasing, and then sometimes for the sake of analysis, it's good to make them decreasing, and you can always achieve that, by the way, by taking the max of all the taking the max of all the betas that follow later. With that, you can make the betas decreasing always, and they still have the same properties that we wanted them to have. So yes, they can be decreasing. For the specific choice that we're gonna have, I think we can prove that they are decreasing, but it's like more like it's gonna be by chance, not by design.
Yeah, I was wondering why we didn't define beta 0 to be equal to 2, because then it seems like it would naturally be decreasing. And you know.
It doesn't really matter because like you can define beta 0 to be any value bigger than 1 and restrict the transition, like the probability vectors to be probably these vectors to be probability vectors. You still get the same set. So any value bigger than 1 would work.
Okay.
Yeah. We're not too worried about this choice. It's hopefully you collect some data and the beta 0 equals the value of beta 0 doesn't matter. Well, actually, it's like you have to choose it big, right? Big enough, because otherwise you may be ruling out the true model, and ruling out the true model would not be good. Like that's the one thing we don't want to do.
Are there cases where being optimistic could be bad?
There are cases when being optimistic is not as good as other choices are. The easier setting for that is when you pull an arm and it gives you information about other arms. Like in a bandit problem, you have, like, let's say 2 arms, and you have, maybe you need 3 arms for this here. No, maybe 2 arms first. You have a suboptimal arm. Okay, you should have like 3 arms. You have a suboptimal arm, and it's very peculiar. Like you pull that suboptimal, like you know that it's never going to be optimal. So it's the restricted setting where the rewards are not arbitrarily assigned to the arms. So you know that the reward is going to be deterministic for this arm. It's never going to be optimal in none of the instances that we might encounter. Maybe there are 2 instances. In one, the first time is optimal. This is zeroth arm. In one, the first time is optimal. The other instance, the second arm is optimal. But it reveals the identity of the optimal arm. And these other arms can only be observed in noise, like let's say with Gaussian noise. Then if you only play the potentially optimal arms, then it takes a long time to discover which of them is optimal, because there is noise and it's not good. But if you play the suboptimal arm only once, then you immediately discover, because it's like, you know, it gives you the index directly of this arm, just multiplied with -1 or something, and these arms have a positive reward. And so you do encounter this situation actually quite often. And the optimistic algorithm, like since we restrict the environment to be such that like we know that this arm is never better than the other 2 arms, an optimistic algorithm would never ever choose this arm. It's really myopic with respect to reward. It's not doing a careful planning and consideration of how information propagates. And so it's almost a miracle that we see it so powerful beyond the standard structureless finite bandits.
Wait, so could you go over why would the optimistic algorithm not pick the worst arm?
Because of my information that I give to you, the optimistic algorithm should use all the information that it has and the prior information that is given to it is that the reward is possibly -1 or -2 for this arm. That's the index of what is the optimal arm times -1.
Yeah.
And the reward of these arms are positive, always. So the optimistic algorithm goes in like, oh, what are the possible words? Well, this could be optimal, that could be optimal. This is never optimal, no matter what the word is.
Okay. So it's too short-sighted in a way. Like,
It's too short-sighted. Yes.
Okay.
It's not planning for information propagation. And so I say it's a small miracle that, for example, in MDPs, where we have all these policies that are, giving information, like you follow one policy, and it gives information about all these other policies. And that with optimism, if you tune it well, you push it hard, then you can get minimax optimal regret in MDPs by and large. That's quite miraculous. Because you would expect that maybe the way the information propagates between the policies, it's, like there is enough structure there to exploit, but it happens that as long as you only care about minimax regret, there's no case that have been identified that this would matter. But for linear bandits, for example, there are simple cases which I like similar to what I described. Like you can somehow embed that into linear bandit. So linear bandit is the case when you have arms. Every arm comes with a feature vector. So that's given to you a priori. You don't know the parameter vector. And the parameter, the mean reward of an arm would be the inner product of the parameter vector, which is unknown, and the feature vector of the arm. So you can plan with the feature vectors then. And in that setting, you can easily come across problems, but there is enough structure in the problems so that optimistic algorithms can lose big time. And if you go to the functional approximation case in reinforcement learning, then that seems to matter, right? Like that somehow suggests that the optimistic algorithms may leave a lot of reward on the table unduly.
I see. Is there like an alternative to that? I mean, I guess there is, but
oh yes, people have been busy. My current favorite is, and many people's favorite in the field is information directed sampling.
What does that do? Like just in a nutshell?
It tries to trade off information gain and reward. So it does as if the word was like you lived in a Bayesian word, and then you can give meaning to this notion of like, what's the information gain given the information I collected so far if I take this action or that action or this policy or that policy. And so you want to trade off that information to the reward that you would receive, and information directed sampling is just says that, oh, you should just calculate this ratio of, I think it's reward squared divided by information gain, the other way around, yeah. Take the ratio and maximize it. So then that means that you want to, I guess it's like information gain squared divided by regret, or like the other. Either way, I'm blanking on it. And so just maximize this. It's not necessarily computationally easy to do this. but it still feels short-sighted because it's just one step, but it's already better. So in the scenarios that I described, it's going to do what it needs to do.
And by information gain, you mean something like how much am I reducing uncertainty, or like?
Yeah.
Okay. So,
Entropy. Yeah. I'm not sure how, how important this is. I'm pretty sure that in some applications it's pretty important. From the perspective of efficient area, large scale, blah, 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 it's a bit unclear whether it's on the shortest path to the end there, but it's definitely a lot of fun to think about it. Any other questions?
How do we compute p tilde?
We'll talk about it. It's hard. People worked really hard to come up with computationally efficient versions of this, which also give you good regret bounds. There is an easy solution to computing p tilde, which is to relax the problem by saying that at every stage in this 8-step problem, the transition probabilities could be different. Then you can just do backwards computation, and it's easy to do that. With that, you lose an extra factor of age, or square root age, or something like that under regret. If you don't want to do that, and probably don't want to do that, then you can work out that it is possible to implement something like this. It's not really this algorithm. That is when it comes to you start from this idea and then you end up with an algorithm that sort of implements optimism, but it's more complicated. So if you implement what I said, which was this relaxed version that starts with introducing this inhomogeneity in the transitions and do the backwards calculation, then you will see how that calculation looks like. And then you look at just those equations, and then you try to remove the need for the inhomogeneity and work out some version of this resulting algorithm that still works. But there you have to redo the proof, and it comes with a lot of extra headache. And that's not easy.
So TensorPlan doesn't begin to address this problem, or?
Oh, TensorPlan, we don't even have any efficient way of we don't know whether you can implement it efficiently. So the TensorPlan is more and it's also for planning. So it was V-star reliability. So V-star reliability is not a really good friend for this online learning. So you want large scale, so you can't really keep models around, or you will want to approximate the models, you will have an approximate model class. And we'll talk about those algorithms. But if you don't want to have approximate models, then you want these algorithms that work with functions only. Then V star is not really a good choice because you can't even do one step look ahead without the model. Like you don't know what's the value of this action relative to the other action if you only have V star. You need some model in that case. Yeah. So tensor plan is just going in some completely opposite direction. It's curious that optimism appears there. Well, it's in a way not that surprising. All right.